Okay, hi everyone, welcome back. Today we have the review stream for TSTST Day 3. So I'm going to go through all three problems and like briefly present the solutions, and that's all. Yeah. Cool. So this was, I should first start off by saying that yes, this test was hard. It was definitely a lot harder than Day 2, for example. So even if it looks easy to follow, it's not actually easy. I think that's the main thing I want to say. Okay, let's go. Yeah, problem 7, the original formulation that test solvers worked on was just like p and p minus constant. I think the fact that we normalized the constant to -1 made the problem more confusing. But maybe, I don't know. It feels like it shouldn't matter, but it's hard to tell without A/B testing. Okay, so let's use this view. Here we are. Okay, so yeah, so I'm gonna first start by writing. Well, the p almost doesn't matter, so I'll just write it as what it is. The equation is like I have alpha 1, alpha 2, x minus alpha n is equal to 1 plus x minus beta 1, x minus beta 2, x minus beta n, where alpha I and beta I are assumed to have absolute value 1. Oh, yeah, I also update that. Sorry, they also have a leading coefficient, so let me put in the leading coefficient. C is some complex number. So C is leading coef. Okay, so because I have these things that all have absolute value 1, what I'm going to do is I'm going to take the complex conjugate of both sides. And when I do so, C bar, x minus 1 over alpha 1. So anytime I have a number on its unit circle, the conjugate is always equal to the reciprocal of the number. We use this all the time when we do geometry in complex numbers, and we're going to use it here as well. x1 minus alpha 2, and so on, is equal to 1 plus C conjugate, x minus 1 over beta 1, x minus 1 over beta n. So let me write this properly, because I wrote the two sides in different ways, and that's not good. Okay, yeah, but here, let me show you something, okay? So if I look at the first coefficient of the top equation, like the x to the n minus 1 coefficient, it's like sum of alpha I equals sum of beta I. Meanwhile, if I compare in the bottom, the x to the 1 coefficient, it tells me that sum of alpha I over product alpha I. So this is like the coefficient that's like the product of n minus 1 of these, so it's this, is equal to sum beta I over product beta I. Oh, I better refresh my algebraic topology then. Okay, so what's the upshot of this? Well, this guy is not equal to this guy because what is it? Yeah. Because when I look at the top equation, they differ by 1 over c. Also, they're not 0 because they're supposed to have absolute value 1. So these two equations, when put together, tell you that sum alpha I equals sum beta I equals 0. So what we get is, so to summarize, by comparing x to the 1 coefficient, or sorry, x to the n minus 1 coefficient, how do you spell coefficient? Of red to x coefficient of green, conclude sum alpha I equals sum beta I equals 0, i.e. both coefficients are 0. Wait, the two expressions absolute value 1 and differ by 1 over c. Isn't that fine if like c equals 1 and the two expressions are... I don't understand what that question means. What do you mean the expression is e to the I pi over 3? Okay, same to that resolved. Okay, so repeating the same argument for x to the n minus I of red versus x to the I of green, we get that all intermediate coefficients are 0. And hence, p has to have a very specific form. P has to be like lambda x to the n plus mu for some complex numbers lambda at mu. And at this point, you're okay, because all you need is for lambda to have absolute value equal to mu, and also mu minus 1. This is like the like once you have p down to like it's a two things, it's very easy to extract because you can solve for the roots explicitly, and the desired condition is exactly when lambda, mu, and mu minus 1 all have the same absolute value. The latter condition you can rewrite if you like as the real part of mu being equal to 1/2, but it doesn't really matter. Why is sum of a1 equals sum of beta 1? Well, you look at the x to the... So you have this equation, right? And you look at the x to the n minus 1 coefficient. By Vieta's formulas, the x to the n minus 1 coefficient is c times sum alpha I on the left and c times beta I to the right. We're assuming these are equal. Yeah, so that'll do it. Like this thing is equal to p. This thing is equal to p minus 1. Yeah. We're not dealing with double roots in a different approach, be 7 minus or 0 plus. Honestly, I have no idea. Ask the... I'm not grading that problem. Thank God. Yeah. But the thing is, you know the products are different, so that implies that the things have to be 0. Okay, and that does it. Yeah. Yeah, this is the complete solution to the problem. All right. cool. So let's go on. Yeah, the author of this problem is one smart cookie. Oh, I'm sorry. I haven't been checking the reward thing at all. What? Okay, good. I didn't miss anything. I'm a little out of it today. I don't know if you can tell. So problem 8 goes like this. And very roughly what's going to happen, like to try to summarize the solution in one word, is like this thing is too big most of the time. So we're going to do the following. Let lambda be equal to the common value. That is more than one word. Okay. Alright, well if you want to condense it to one word, you can say, right. I don't know. Sorry, size is better. Anyways, let lambda equals the common value. So I'm going to look at the quantity sigma mn and claim that it's usually too large. And claim 30-second ad break. I'll do it after the problems. Okay, the reason is that when I look inside the divisors of mn, there's two kinds of numbers I'm going to see, at least. So there's divisors of m, and then there's also divisors of n times m. Like every divisor of n times m will also divide mn. That's called a sigma, little sigma. So because of this I get a bound of sigma m plus sigma of n times m. Except this is almost true, except that these two overlap in exactly one number. The number m is always counted twice. So this is a bound that you can write. And now, well, okay. I can write out what it should be equal to in terms of lambda. This is equal to lambda times m minus 1 plus 1 plus m times lambda of n minus 1 plus 1 minus m. Sorry, that's a typo. Or no, it's just sloppy. And when you compute this, lo and behold, you will find that this is given exactly by lambda mn minus 1 plus 1, which might look like a miracle unless you happen to know what the answer is, which I'll tell you now for the people who haven't noticed. Lambda is the common value, so like there's these equations that are equal, and I'm going to let the common value be equal to lambda. Yeah, this looks like a miracle unless you know what the answer is, and the answer is that if m is the power of a prime and n is the power of the same prime, it will always work. And that's why this estimate makes sense to do, because that's why this estimate makes sense to do, because it's like, well, it's preserved at equality. Like when m and n are of this shape, then this less than or equal or greater than equal to sign is actually an equal sign. And yeah, so when m and n are both prime powers, the greater than equal sign is actually exactly an equal sign, and so that's why you're not surprised when you get the quite right quantity at the end. Lambda a variable or is a defined value? I don't... It is a value that depends on m and n. Yeah. Okay, so what we've learned is that we knew that this greater than equal to sign works whenever m and n are both prime powers, but now we have an analysis that says, okay, if the problem is going to work for m and n, then this has to actually be an equal sign, meaning every divisor of mn must fit in the following Venn diagram. this is divisors of m, this is divisors of n times m, and they intersect only at the number m. Okay, and you can run the same argument with n, and it will sort of just solve the problem. Like, you can check that the only way this ever happens is if m and n are like the same thing. To be more explicit, let's say if p was a prime which divides m but not n, let me flip it. N but not m, then p does not fit in the Venn diagram. And similarly vice versa. Also, if, let's see. What happens if like m and n have the same primes but there's more than one? If p and q are different primes which divide m, then there's going to be a prime that doesn't fit in the Venn diagram. Or there'll be some divisor that doesn't fit. Let me think what it is. I'm suddenly blanking. Someone help me out here. Okay, so 15, 15, 25. Q over n. Choose p dividing mn and TSTST stands for Team Selection Test for a Selection Team. Okay, let me do it this way. Suppose p divides m. So any prime that divides one divides the other. If there's two different primes, then p to the alpha plus p to the vp of m plus vp of n does not fit in the Venn diagram. Okay, there we go. Yeah, basically, like, the Venn diagram thing is so unlikely that it only happens when m and n are powers of the same prime. So that's the final answer. Yeah. We were glad that people did not complain on the AOPS forums that this was a combo problem, because it is kind of combinatorial. Thank you, Fresto, for 100 bits. You're welcome. I haven't been able to write napkin stuff for like forever now. I hope I can get back to it at some point. Yeah. Yeah. Oh, I never defined that command. I'll have to define it later. Or I can just define it now. Where We're doing it live. Can someone please explain it? Give me a moment. Hey, okay, it works. Also, I need to update the UCMO command. Someone pointed that out. I'm very easily distracted. A, B, G, G, and W. Okay, let's go on. So, problem 9. Problem with 10 million fireflies. Okay, that went horribly. It sounded much better in my head. 10 million fireflies, because I hate goodbyes. Yeah, I think the original proposal was sent in with like 1 million, and I was like, no, you gotta make it 10 million. So then it was 10 million. 10 million fireflies. Okay, so first let me tell you what the answer is. I think the first thing I should say about this problem is that most people don't get the answer correct either. Like, if you try the 2-dimensional case of the problem, you might be inclined to think the answer is 500,000 squared. But it's not. It's the answer is 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3. Yeah. Which is also just 10 to the 14 over 3 floor. Okay. So where does this number come from? It's really easy if I just tell you the instruction. So we're going to consider 3 lines in R3 that are the vertices of an equilateral triangular, not vertices. They form an equilateral triangular prism of infinite whatever. Okay, just take 3 lines that look like this, and then on each of them you put about 1/3 of the fireflies. So here you put 3, 3, 3, 3, 3, 3 fireflies. Actually, hang on. I should do these in different colors, just to be extra. Boop, 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 boop. Okay, we're gonna do this. Done, done, done. Do. Oh crap. Do. Oh, that doesn't look right at all. It was better before. Okay, there we go. Cool. So here I'm gonna put 3, 3, 3, 1, 2, 3, 4, 5, 6, 7. Just put them anywhere on this line. And there are no restrictions. That is correct. That being said, they do still have to maintain the condition. 3, 3, 3, 3, 3. And here I'm gonna put 3, 3, 3, 3, 3, 3, 4. So you distribute them about equally, and then you say 2 fireflies are friends if they're different colors. Then what I can do is I can take all the blue fireflies and then reflect them downwards, like 1 by 1, to like... that's really hard to read actually. Like, you can hold all the red fireflies fixed and all the green fireflies fixed, and then reflect all the blue fireflies. This is possible because all the friends of the blue fireflies are red and green, so you just take the reflection through that plane, and the distances won't change. And you can keep reflecting the entire lines 1 by 1, and by doing this, you will eventually be able to move this. You'll be able to translate the triangular prism as far as you want in any direction. Yeah. Okay, so that's the construction. And you can check that when you do this, the number of friendships you get is actually given by the formula I claimed it was. And some people have already recognized this. This graph, the graph that you get from the friendships as a special name, it's called a Turon graph because it's the largest graph that doesn't have a K4 in it. In our case, a K4 would be a tetrahedron, just like 4 fireflies with mutual pairwise friendships. So you might be tempted to claim that there is no K4. Well, the first thing you would think is maybe there's no K4, and then you're like, wait, that's silly. Like, no, like if you just have a K4, you can have a K4, and that the fireflies can just move. Yeah, they can move. And you might think, okay, well, maybe if you have a K4, then it's not optimal. And this is true, but it's only true for n large enough. So 3VT is already mentioning that for 5 fireflies, the optimal construction actually has a K4 in it. So this will not terribly hinder us, but it's important to keep in mind that we will actually need the fact that 10 million is like pretty big. It will not work if 10 million was replaced with like 5. So what do we do? So let's suppose there is a K4. So I have 3 fireflies that look like this that are all friends with each other. So suppose K4. Man, I want to move that tetrahedron up just a little bit. Okay, yeah, so suppose there is a K4. Then what can I do with this? First I wanna... Okay, firefly. Okay, sorry, I lost my train of thought. Oh, I missed a bunch of shoutouts too. So shout out to Chenis199 from AOPS user 305, to VEnhance from AOPS user 305, and CNC Math also from AOPS user 305. I'll do the ad break after I finish talking about this problem. So if there's a K4, then here's the claim. Claim there are at most 12 fireflies, and the number 12 won't really matter, other than the fact it needs to be like not too big, but there are at most 12 fireflies that have more than 2 friends among A, B, C, D. That's the claim. And the reason is that what we're gonna do is we're gonna suppose there is a firefly called E, which is friends with, say, ABC. Alright? So this guy, this guy, this guy. The official solution gets a bound of 12. I think there are other bounds that you can get. depending on how you vary what exactly you say in the claim. But yeah. I don't know. I got the official solution gets a 12. Thank you, Space Sam 2005. Subscribed for 3 months. So in this thing, in this picture, what happens is I have 2 tetrahedrons. 12 is not really special. 12 is just the number that comes out, and I'll explain why. So in this picture, if I have a firefly E, then I have these 2 tetrahedrons. So what I'm going to do is, as the fireflies move, these points will move. And ABCD will always be a tetrahedron with a fixed shape. Like the shape of ABCD will never change. So I'm going to treat that as a reference frame, by which I mean I will always kind of treat these points as not moving. So if D reflects across ABC, for example, the way I visualize this is actually everything else reflects. So ABC stays put and ABCD stays put, and then E moves somewhere else. For this reason, I want to draw a second. E is sort of in 2 places relative to the tetrahedron, like E1. And so relative to ABC, E can be in 2 places, like this E1 or that E2. So again, I'm treating ABCD as a fixed reference frame. And I'm considering the position of firefly E only relative to ABCD. So I just pretend ABCD never changes. Okay, so what about this? Well, first of all, I should say, I've assumed that E is friends with ABC. So this is, without loss of generality, E is friends with ABC. There's 4 choices here actually, not because I could pick any of these 4 vertices. So far I haven't done any work yet. I'm just saying stuff without loss of generality. Now, let's say that, consider a moment when A moves. At a moment just before A moves, it means that wherever firefly E is, it could be either E1 or E2, but it has to lie in plane BCD at that point for firefly A to move. So either E1 is in BCD or E2 is in BCD. And then similarly for CDA, or ACD, and similarly for ABD. What's the motivation for this? So the tetrahedron is the big thing. Like if you have a tetrahedron, the shape of that tetrahedron never changes. It's sort of considered fixed. And this, what happens if you have this shape, the lemma is telling you about tetrahedrons that share a face. It tells you that doesn't happen too much. So the way you can phrase this is that tetrahedrons don't share faces often. They could, but they usually don't. And you can imagine that having a tetrahedron share a face is really constraining. Yeah, actually, I should put that into the official solution as well. Okay, so anyways, if you look at these things, by pigeonhole, one of the points is in 2 of the faces. Like maybe we have this one, and that one or something. Let me do it in green actually. And if this is true, then that tells you E1 is given exactly by the intersection of CD with the plane ABD reflected. Like depending on which 3 statements is true, you'll be able to pin down E1 and therefore E2 exactly. And the number of ways for the statements to be true is 3. You actually can't have E1 in all, you can't have like them all in the upper row because that would imply E1 equals D, and fireflies don't occupy the same point. It'll cause problems. So, yeah. So, therefore, there's at most 12 possible positions for the pair E1, E2 and proof of claim. Great. So now all I have to do is do the finishing. Once I have this claim that says that tetrahedrons don't share faces often, the rest is just bounding. What I'll do is I'll let Fn be the max with without K4. So the maximum number of friendships you can have without a K4, and Gn be equal to the max with K4. And we know actually Fn is exactly given by Taran's theorem, and is given f of n is known exactly as n squared over 3. And so what about g of n? Because of this, you can, if there's a tetrahedron, you delete it. And it gives you a bound where this is like 2n plus like some number, I'm just going to look up what the number is because I don't want to mess it up on stream. But basically you delete the tetrahedron and the bound will be good enough because it's about half the edges are there. Yeah, the bound comes out to like 2n plus 10 plus max of fn minus 4, gn minus 4. And if you iterate this bound a bunch of times, it will eventually tell you that g of n is like approximately n squared over 4, which is smaller for n large. So I won't do that algebra on the board because I don't think it's possible to follow, but you can see the details posted on AOPS if you care about that detail. That part is just calculation, so I'm not going to belabor it. But the point is, once you have the answer, you should suspect that tetrahedrons are important, and the key lemma is that tetrahedrons don't often share faces. Once you prove the key lemma with really any number, like this number 12, it doesn't matter. The proof would work equally well if this 12 was replaced with like some larger constants. It's just, you just want there to be at most finitely many fireflies that form a tetrahedron. And if that 12 is increased, all that happens is this 10 becomes some larger number, but that won't change the fact that the overall order term is n squared over 4. How do you get the ideas for bounding based on tetrahedrons? I think it's not, I don't even think you care that much about the bounding to start. I think you just want to say like, you know tetrahedrons cause problems, because if there were no tetrahedrons, you use Taran and you're done. And you know that for small values, the tetrahedrons are okay, but it seems like for large values, the tetrahedrons get stuck. And what you say is like, okay, I claim that tetrahedrons don't share faces often. And if that's true, then it means that the density, like, it means that the tetrahedron vertices are about degree half. Like the degree of, in a tetrahedron, the degree of the vertex is about n over 2. So overall, that graph will have degree total number of edges about n squared over 4, which is less than n squared over 3. And, well, maybe that's a bit too global, but I think the point is like, you're like, okay, what happened, like, because tetrahedrons don't share face often, if you can show the tetrahedron has a most half-ish degree, then you can just take out the tetrahedron and induct down. And that's exactly what the solution does. Yeah. Because the n squared over 3 is actually pretty big, is the thing. Like, in the Taran graph with 3 parts, all the vertices have degrees about like 2 and 2/3 n. It's more than you expect. Yeah, like I think the thing that surprises people most about the problem is not the proof of the bound, it's the fact that the answer is so large. Right. Like on the test, like when people work on this, nobody accidentally guessed a number that was too large, but lots and lots of people had constructions that were like much worse than either like worse in the sense it was n squared over 4 or like even worse in the sense that it was like linear in n. The big surprise is that the answer is not only quadratic in n, but the constant is as large as it is. It's like 1/3 out of a possible 1/2. Yeah, like the Toronto graph with 3 parts is pretty dense. Okay. Alright, so that concludes the review of TSTST Day 3. Hope you found that a little informative. The official solutions will go up onto my website pretty soon. I want to do a bit of polishing with them as I work through things and improve the remarks a little bit. But it shouldn't be too long before those go online. And, right, hope to see you next time. Good luck, have fun.